Welcome back here. So a little unexpected, but we hope we hear Peter, and also we will hear from Mark. Talks that we had free up more time, more tomorrow once the machines, or hopefully we have access to the machines, come back, we have more time for the hands-on. The plan is to, start with Peter. This is an hour-long talk also, and then we go into a coffee break and hear from Mark.
All right. I just had 20 minutes to finish the presentation, so please bear with me if there are typos or something weird, or I all of a sudden stall and can't figure out where I'm going. So Christiana asked me to talk about physics dynamics coupling. I'm probably going to be using acronyms that I don't define in the slide deck, but you probably heard CAM, Community Atmosphere Model. That's the modeling system that you're working with here, developed at NCAR and with partners. And then MPAS is the model prediction of across scales. So about 6 months ago, I was asked to give a town hall talk to all UCAR, NCAR staff, including all job categories. And I wanted to talk about what I was doing with physics dynamics coupling. I was trying to figure out how the heck do I explain this so everybody gets like an idea of what I'm working on. And I really like to use figure of speech. So I tried to depict what the daily life of a model developer looks like. So I asked ChatGPT. I have the paid version. And the first image it gave me was the machine room and something that looked like the Titanic. And I thought that was a little bit too dark. So here's like a 1980s machine room. But it's kind of what we do as model developers. We have the engine here using figure of speech as our modeling system, and we're all down there fixing things with their break, and sometimes we take big components out and putting new ones in. And as we do that, like we don't want the thing to leak. We don't want any mass to fall out of it. We don't want heat to leak out of the system either. So like we want some kind of conservation in there. But obviously, you all really trained in this area. So let me get to the non-figure of speech explanation here. So if we want to build a, did this thing just go forward? Oh, there, okay. So to talk about physics dynamics coupling, we need to first define what are the different components of the system. And here one component of the system that you know very well is the dynamical core, where you start with an advection scheme, you develop your numerical method, then you go to a shallow water model, then you go to a 3D hydrostatic model, maybe you go non-hydrostatic, then you start adding moisture. So like 15 years later, maybe you have a full dynamical core. And even at that point, when there's always stuff where you need to go back in and tweak something in the die core when you're running with full physics. This is a very long process. So that's one of our components. The other components is physics, and that's full of a lot of stuff. So here's an example from CAM. We have cloud microphysics, loosely speaking, telling us, when do we have phase transition between liquid and ice, or evaporation, and so on. We'll have a radiation scheme in there. We'll have some parameterization of unresolved gravity waves. We'll have deep convection, and then we, most of the time, have shallow convection and turbulence in a different scheme. And in CAM, it's this club scheme that I'll come back to later. And then we also have like an aerosol module, and so on and so on. So when we think of physics dynamics coupling, please think of the full system. No? So as described by Marcus here, the challenges associated with bringing together all the various discretized components to create a coherent model will be referred to as physics dynamics coupling. So that includes coupling to the surface components as well, not just die core and physics. Okay, so let me walk you through a typical, or not a typical, but a time loop that we use in this building. So first we run the dynamical core. If it's a 1-degree model, we run 30 minutes forward. Then we pass that state into physics. Then physics will take that state and run a parameterization. In our case, it's deep convection. And then after that, we start communicating with the surface model. So we will tell the surface model how much water fell out of the atmosphere, for example. And the surface, or the coupler, would tell us, what is the SSTs coming in from the ocean, or how much evaporation, so how much water vapor is moving into the atmosphere, et cetera, et cetera. Then we go back into physics and somehow apply these tendencies, and then we run gravity-based parameterization, every other physics time step we run radiation and so on, and then we basically go back to A in this loop and somehow add the tendencies from physics back to the die-core. So that's an example of a time loop in a full modeling system. So I've stolen these figures here from the last DCMIP, where Peter Caldwell gave a really good talk on physics dynamics coupling. So anywhere in the model, you can have process split or time split, and it can happen in physics or in the die-core and the way you couple the two. So the time split or sequential split update is what we use in CAM physics. So that means you take the state, and then you run a parameterization, and then that parameterization then updates the state. And then that state is then fed into the next parameterization. So that means that the parameterizations feel each other. The order actually matters. Then there's another example. Peter Caldwell put CAM microphysics in there, but you could also refer to WRF physics or MPAS physics, where all the parameterizations are giving the same state. Then they advance forward one time step, and then you collect all the collective tendencies, give them back to the die-core, and then the die-core then applies these tendencies. All right, just a couple of remarks here to get you thinking about stuff we have to think about with physics dynamics coupling. So as I mentioned before, like deep convection will produce in some grid cells precipitation that's computed before the coupler. Then we'll have shallow convection that may also produce some precipitation that's computed after the coupler. So therefore, there's a time loop here. No? So if you so the precipitation that the coupler sees will be convection in the current time step, but then we'll receive the precipitation from the shallow convection and other processes from the previous time step. So everything is always a little bit out of sync there. So we have to figure out now, when do we sync up things? And Adam kind of got to this in his presentation as well. You may also ask the question, when in this loop is the state most realistic? So that really matters for data assimilation or end users. When should you do your I/O calls to write temperature and pressure to disk? We're die-core persons, so of course you should be after the die-core, which in some sense is true, because what does a die-core do if you bring it out of balance? What happens if you add heating somewhere? You've seen it in your test case, that you get these gravity waves that radiates out. The atmosphere tries to get back into geostrophic balance. So in some sense, you can say the die-core gets rid of that, some of it. But the problem is that you can get supersaturation, so relative humidity can go beyond 100%. So that's maybe not the best place. Should be before the cold to couplers, or before we felt the surface components, or right after? So there's a whole science associated with that. And if you want to read more about that, so I added these. You can click on these hyperlinks in the talk if you want to learn more about it. But as Adam was mentioning, we want some adjustment to take place to take supersaturation out of the state before we do data assimilation or write to disk at a minimum. All righty, now let me go to this somehow here. Like how can we add the tendencies to the die-core? So first, let me describe what the tendencies typically are. So typically, the parameterizations will have some kind of tendency on the wind component. So it could be drag from gravity waves. So usually we have a tendency of the U and V components. There'll be some kind of tendency associated with heating. Most modeling groups use temperature tendencies as the variable to communicate that. I will get back to that in a moment, that I don't think that's a good idea. And then there'll be tracer tendencies, how much water vapor is lost, or liquid, ice, chemical species, et cetera, et cetera. So let me just give a simple 1D example, similar to what Pete showed earlier. Let's assume we have a cloud here. So this could be cloud liquid, that yellow line there. And let's say that physics decided to evaporate some of that cloud. So if it evaporates the cloud liquid goes down. So these blue arrows here, that will be the tendency from physics. So one thing you can do that's done with FV free and FV is, as soon as you get into the die core, let's subtract these tendencies. Then you end up with that dotted line there. You see the cloud liquid has gone down. And then your die core, MPAS, FV, whatever, will then advect that distribution. Let's say the wind is blowing that way, so things will move over there. So that's one approach. We put that into, or I think marked it, we put that into spectral elements. We kind of saw some problems. So my colleague Dave Williamson said, why don't you look at the absolute surface pressure tendency? That's meteorologists like to look at that just to see if there's noise in the model. And that's what you see on the right-hand side. It is a one-year average of that field. And for those of you who are working with the CubeSphere models, this is what CubeSphere grid imprinting looks like. So, and this is the vertical velocity field, which is one of my favorites for looking at noise in the fields as well. So what's happening here, since we're using a long physics time step, is that the tendencies you're adding to the die core is a big shock to the die core, and it just radiates away gravity waves that are unphysical for the most part and creates this noise here. So we have a problem. So one solution could be to reduce the physics time step. I think that's a really, really good idea, but it's also really, really expensive because our physics is very expensive. So it's not a practical solution for expensive physics packages. We can also say, well, why don't we divide the physics tendency into chunks and then add them throughout the die core integration? So here's an example of that. So now these blue arrows, if I've done it right, should be half the length of the blue arrows that was on the previous slide. So when we go into dynamics, we add half the tendency, and then we let the die core run for 15 minutes. And then we add the other part of the tendency. And then we do another 15 minutes of advection and whatnot. If I now compute the same fields as we had before, then they look like this. And that looks much more physical to me. I can't see the grid in these solutions. So you might think, well, problem solved. And it is, if you don't care about conservation. And for those who know me, I really like conservation. So what you can do is, let me just see how I ordered this. I'm sorry, I messed up the slides a little bit. Yeah, so just to show you the conservation issues, I computed this a very long time ago, but this is if you use this method here where you add the tendencies. Sorry, let me go back. I realized I should have explained this part here. So the problem that, I didn't explain what the problem was. So the problem is, for this grid point right there, now that we've advected for 15 minutes, now the cloud liquid mixing ratio is 0. But I'm still applying the tendencies in the same point right here. So what happens is you get an undershoot, you get negative cloud liquid. And that's not good, that's not physical. So this is a 10-year average of how much you lose, or in a way add to the system. So if you just go in and say, okay, I'm just going to chop this negative value here is unphysical. So I violate mass conservation. So I should have removed water from the system, but I didn't. So it's actually a source, water source to the system. So if you do a 10-year run accumulated, then you would have added about 0.2 hectopascal of mass to your system over 10 years. So you see, this is not a problem for a short run, but if you start running 100 years here, we're starting to really add to the weight of the atmosphere. That's not desirable. So what we can then do is combining the two tendencies. I'm trying to figure out, there's one thing missing here. Okay, well, what you can do is to try, let's just assume that U, V, and T are causing noise issues if we add them in one go. So we dribble in those tendencies, so divide them into chunks and put them in there. And then we just do the state update, which is conservative. That was the very first method I showed you for tracers. Then the mass budget is close. So if we do that, we get this solution here, which again looks physical. This was before Mark and I solved noise issues around topography for those who are staring at those wiggles of the Andes. But we've improved a lot on that since this paper was published. Alrighty, so just to summarize here, we have the two ways of in the physics packages, and you can do it in a dicore too, of adding tendencies to your state. So I mentioned to you we can run all the parameterizations from the same state, which is somewhat easier to implement, and things can actually run in parallel. I think DOE has looked into that because you could separate it on different tasks and just let them run. But there are conservation issues associated with that. So your state can become unphysical, so that's a problem for long simulations. And another thing is that the different processes represented in the parameterization do not feel each other. So you kind of, if you just add them afterwards, you can get this competition between parameterizations that's not resolved in physics. And then the other approach, which we're using in CAM, so it's obviously superior. The state remains physically realizable because if the parameterization are designed to do that, because each parameterization feel each other. And then you can also resolve some of these issues where parameterizations are competing with each other. So that's what I refer to as double counting. The problem is the order really matters. So you have to figure out what should the order of physics be, and that's not necessarily straightforward to figure out. What Peter Caldwell also pointed out in his talk here is that these ways of coupling dynamics on physics are at best first order. So he kind of made this provocative statement. Why having high order dynamics when you're just doing first order coupling with physics? So you destroy all the high order that you're trying to achieve in the dicore. So people have looked into this, and I won't go into it, but there's definitely two papers here you can look up. There's one here, one from ETH, where they look into quite a few different higher order ways of coupling physics and dynamics, and the UK Met Office has also done some work on this. I would like to just highlight here, and I also mentioned it too, just keep in mind all of these errors that I've been talking about up to now will all get reduced if you just reduce the temperature or the time step for coupling. So that's important to keep in mind. Another challenge with physics dynamics coupling is our variable resolution applications. So here's an example from one of our grids that Adam put together, where we go down to about 12 kilometers over Greenland, which is part of Denmark still. So what you do here is that we run with the physics time step that matches the high resolution area. So if this is 12 kilometer, we might be down to like a 5-minute physics time step. The problem is that we're also running a 5-minute physics time step in the coarse region. And our physics, at least the CAM physics, is quite sensitive to time steps. So that means that your coarse resolution solution, its climate might not match what your regular uniform resolution model gives you. So that's, I would say, like an unresolved problem with variable resolution applications that I'd like you to be aware of if you choose to use those. All righty, back to the machine room. I've talked about, highlighted mostly, there's mass conservation errors, and you may pose the question, well, what about heat in the system or energy? So I embarked on that quite a few years ago. Dave Williamson was doing work on it, and I got interested in it. And Kevin Trenberth also was interested in it from, he was looking at reanalysis and kind of seeing big errors in energy budgets and starting to ask a lot of questions I couldn't answer. Unfortunately, this is really a big can of worms. Yeah. Okay. All righty. There's a shelter in place, so don't move. I don't know why. So I couldn't answer these questions that Kevin was asking me. And I'm like not a super intelligent person. So what I do when I run into a problem I can't solve, I seek help. And I was really, really lucky that my colleague, Nicholas Keflahan at McMaster University, he called me up and said, hey, we can apply for this Banff International Research Station. Everybody has to pay for their own tickets, but then they provide everything else. That would be really cool. Do you have an idea of what we should talk about? And I said, yes, I have an idea of what we could talk about, physics dynamics coupling. So we brought together, you can see a lot of faces, or recognize a lot of faces there. So we brought this together, had pretty wild discussions for a week, and then we had, I don't know, 20, 30, 40 Zoom meetings during COVID, putting together this paper. So what I'm going to talk about next is mostly in that paper. A little warning, it's 55 pages, and the appendix is 25 pages. The complicated thing about energy is that, loosely speaking, it kind of encompasses everything that's going on in your model, because you have kinetic energy, you have more kinetic energy the faster you're moving, for example. You have potential energy, depending on how high up you are. And then you have some kind of internal energy or enthalpy that depends on temperature. And the energy equations for the atmosphere, I'm glad Dave Randall showed some of that, depend on all kinds of assumptions. So here, I've just assumed a dry atmosphere. So in the literature, there's no ambiguity of what energy should be in a dry atmosphere. But as soon as you add moisture, all hell breaks loose. So it's very, very convenient if you have a z-based vertical coordinate, and Dave showed this equation here, to have a top of the model that's just a rigid surface. In that case, the energy equation for the frictionless or the adiabatic equations is that one that's written right here. So kinetic energy, internal energy, CVT, and potential energy, the G times Z, the phi terms there. And then rho is density. And then we integrate that over the entire sphere. So when you do that, there's a lot of terms that cancel out. So that's why we're only left with these terms here. If you look at local energy, there's a bunch of extra terms here. So this is just globally integrated over the entire domain. When you work in pressure or mass coordinate, I shouldn't say pressure, it's really mass coordinates, but with a top pressure at the top that's 0, then your equation looks like this. And through integration of parts, the CVT now became a CPT. And the phi there became phi s. And please be aware that K CVT plus the potential, that's the true local energy density. This is not the true local energy density. It's only true globally integrated. So all of that was derived in this really nice paper from '74 by Kasahara, who worked in this building. And please be aware, if you're somebody like Owen doing deep atmospheres, you've got to change this for deep atmospheres. So you have to put whatever assumptions you're doing into this. So I have to go into a lot of thermodynamics, which I have a really hard time with. So I was really happy to see this quote that I actually put in the paper from Richard Feynman, which I believe all of you know. And he said, you know, the subject of thermodynamics is complicated because there's so many ways of describing the same thing. And that's also what you will find when looking through the literature. And the way we wrote our paper was to write it in a form that was like readable for atmospheric model developers, because we could have formulated in a different way that would have been more elegant, but I'm sure I would have lost most of the readers doing that. So just keep that in mind as we do all this thermodynamic stuff. So an issue that happens in physics dynamics coupling in relation to temperature tendencies, I've tried to describe this. So if you're empaths, you're using the z coordinate, so you're in a constant volume model. If you are FV free, or spectral elements, or a lot of other, or ECWF, IFS, you're on the right-hand side here, you formulate your vertical coordinate as mass coordinates, so that's a constant pressure formulation. And that has consequences when you add heating to the system. So let's just assume we're in physics, with constant pressures. So the second terms here on the right-hand side, they're gone. So from the first law of thermodynamics, if you add heating to the system, say there's convection, or there's phase transition, something that creates heating, that goes directly into enthalpy, which is CPT. If you do that for a constant volume model, add heating to the model, that goes directly into a change in internal energy, which looks a lot like the enthalpy over there, but it's a CP instead of a CV. And those two constants, in case you haven't memorized them, they're different. It's 1 kilojoule kilogram Kelvin, and the other one is 0.7. So you have to be really careful there with those assumptions. So what can happen if you're not careful is a physics package, the ones I am aware of, they will all return a temperature tendency. So the question is, you know, when you go back and apply that to the dicore, you have to be careful, because this temperature tendency was computed on a constant pressure assumption and not volume. And that creates this scaling. And I was told that the WRF developers forgot about this when they were coupling WRF physics with the WRF dicore, and they were seeing really crazy stuff until they realized that they needed this 1.4 factor in there. So that's one way things can go wrong in physics dynamics coupling when you have this energy view of things. Another thing is how do we treat condensates? So traditionally, large-scale models, large-scale physics packages, and dicores, when they talk about a unit of air in terms of its mass, they only include the dry air and water vapor, so only the gaseous components of air. High-resolution weather models, you get to a resolution where the weight of the condensate, so that's a non-gaseous part of your parcel, so you can have cloud liquid, ice, grapple, snow, whatever microphysics folks want to put in there. And at really high resolution, they actually carry significant weight. So this can be a difference in what's included in the weight of the atmosphere. So if you take MPAS dynamical core or the N covers and the spectral elements, it has all these in the mass field, and CAM physics only used to only have that, so you have a discrepancy. It's not really a big deal at low resolutions. I computed what is the energy imbalance caused by this in a long simulation. And you get this signal here, which is 0.009 watts per meter squared. So that's very, very small compared to like climate change signal, which is like order watt per meter squared, and then very, very small compared to local tendencies that could be like 100 or more watts per meter squared. So very small, but a discrepancy nonetheless. So the other thing that can happen, so I told you about the CP-CV issue. The other thing that can happen is that the die core has a more comprehensive enthalpy or internal energy formula. So a more advanced way of describing the heat capacity is this generalized approach, and it follows the same formula if you also have dry air split into all its different dry air components. That's important for high-top modeling. But here I just written it out for the water species. So you'd be summing out all the water species times how much you have of it. That would be a generalized CP. So that the SE dicore here at NCAR uses that, and then you may have that in chem physics. We assume CP dry for everything. Another discrepancy. Here's just an example of how I've attempted to fix this discrepancy in Chem 7. So in terms of coding, or not in terms of coding, I make the assumption, and you don't need to do this, but I just say I want to conserve the energy that the die core conserves. And then I fix the discrepancy between physics and the die core. You could also do it the other way around. There are arguments for doing that. The way I've coded that is I have this generalized variable, and then depending on the die core, I put in there what I need to compute its a thermal energy term. So like for FV, it's enthalpy, CP dry. For SE, it's this generalized enthalpy formulation. And for MPAS, it's this, I don't know what it's called, constant kappa approximation. So that uses that formulation. So what I do before I get back into physics, and I just copied this from the code because I didn't have time to type up the equations, but what we do is that the physics set is telling the die core I added CP dry times a delta T, which is a heating increment, to the state. And I want to make sure that the die core sees the same increment in energy. The problem is that the die core uses this different definition of the CP term here. So what I do is I scale the temperature tendencies, so that's what's happening down here, so that the energy increment in both systems is the same. Sorry if that's a little hairy, but that's what I do. So in that way, the energy fixer that fixes energy errors in the system will be consistent with the die core, and it sees the heating that the physics was seeing. So that's an attempt at making things slightly more consistent. So that means for MPAS, for example, we're fixing the energy with a hydrostatic energy that's consistent with hydrostatic MPAS. So I'm just running through everything that can go wrong here. So I'll continue running through. So this is something I had fun with bringing MPAS into to CAM. So now we have a constant volume die core. We have a constant pressure physics. And the way MPAS has chosen to specify its state is different than how CAM physics specifies its state. So as Dave was showing this morning, they use this modified potential temperature. You have your velocity components of perpendicular to the faces of all the Voronoi cells. You have dry density, and you have height, which that coordinate stays fixed in MPAS, and then you have all the dry mixing ratios. So that's the prognostic state, and from that you can derive whatever you want to derive. But you can obviously do, you don't need to do that. You could choose another prognostic state, which CAM physics does. It has temperature, velocity components, has pressure at the interfaces, and then it has moist mixing ratios for water species, and to make everything more confusing, all the chemical species using a dry mixing ratio. So you have to convert between these two states. So one discrepancy between this system is that Z has to be diagnosed on the right-hand side here. So if I just use the CAM machinery as is, when I do the physics dynamics coupling, then then I can compute, okay, MPAS has a Z that's fixed, it won't change. And then I can compute what Z comes out of CAM physics that's derived. And I've plotted the discrepancy here at different levels in the atmosphere. So at 500 meters, it's like less than half a meter discrepancy, so pretty small. If you go up to 10 kilometers, it's about 5 meters. If you go up to 25 kilometers, about 50 meters. So it's small, but not like super, super small. But that's a discrepancy that can happen if you don't think carefully about physics dynamics coupling. Another issue you run into is that MPAS is non-hydrostatic. Chem physics is hydrostatic. I don't know how much more I want to say about it, because I don't know exactly what non-hydrostatic physics would look like, but that would require a lot of work, but it probably would make sense for like deep convection and so on. But that's another discrepancy that you should be aware of. All right, how am I doing on time? Okay, I'm pretty close to done. Another discrepancy. I could go on for hours. All right, so this was discovered by Chris Golas at DOE. So we have this very fancy boundary turbulence scheme called CLUB. I think I have the acronym spelled out on the previous slide because I haven't memorized it. Well, I don't have it. You have to Google it. So what happens in CLUB is it has chosen to use a conserved variable under which it's operating, and that's, should have shown that on the previous. That's this theta L here, which is temperature over the Exner function, latent heat of vaporization over Cp times 1 over the Exner function times liquid. So don't worry about the details, but just worry about this is the conserved variable that's used in the formulation of CLUB. And Vince Larson, who developed this, said, well, I just chose this because that made sense to me. So back to the quote from Richard Feynman, you choose what's convenient for whatever you're working with. But he told me afterwards, well, I could have chosen what's consistent with CAM, which would have been enthalpy, CPT, instead. So what then happened, and Chris Golas figured this out, that if you integrate the energy equation, now I've included latent heat terms that I didn't show before, but if you integrate them in the vertical, then equation 158, that's from the 100-page paper. Then you get that equation there with CPT, blah, 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 integrated in the vertical. And then you get exactly the same formula for CLUB, but it has this 1 over Exner. So they don't conserve the same energies. Is that a problem? Maybe. We fixed it somewhat in CAM, but this is the energy tendency due to this discrepancy for a 1-year run. So it's 0.4 watts per meter squared globally, so it's not tiny. What do people do? Well, we just go in and fix it. No? So CLUB put in its own column fixture. We had a little temperature so that the two match up. That's a ad hoc fixer. Was it? There it is. Cloud layer unified by binormals. Okay. I'm sure you already knew that. Huh? Alrighty. So I hope I've given you an idea of these thermodynamic inconsistencies that are in models, and there are many, many, many more. Like, you should really ask the physics dealer, what assumption did you make when you derived your scheme? And hopefully one day we can make the same assumptions. Is all hope lost? No. There's some really smart people who have been thinking about it. So Chris Eldred and John Fubin from University of Exeter. I actually asked Chris Eldred to put this in the appendix of the paper, which would have made the appendix another 20 pages probably, but he published his own paper, which is good. So I've stolen that from here, and I won't go into the details, but the idea here is that you define a function from which you can derive all your variables like pressure, temperature, volume, et cetera, et cetera. So that can be internal energy, enthalpy, Gibbs free energy, Helmholtz free energy, et cetera, et cetera. So they're listed out here. I defined the variables here, but I just want you to get the idea. You can define this potential from which you can then derive pressure, temperature, et cetera, et cetera. And you made all your assumptions over here. So whatever assumption, thermodynamic assumption you put into your system, they are in this. You will always get consistent variables derived from that. So that's the basic idea. Whether you should do Gibbs free energy or Helmholtz or this or that, ask these guys. Okay, so this is just stolen from the paper. So we just listed all the kind of energy errors that we could think of that are in, for example, the CESM model, but also other models. So I'm just going to quickly run through it. Don't read it all. Dynamical core energy dissipation errors at 1 degree resolution, about 0.1 to 1 watts per meter squared. Good news, increased resolution, it goes down. It actually converges. Temporal physics dynamics coupling errors is what I showed before, dribbling, state update, blah, blah, blah. It's 0.4 watts per meter squared, so not super small. There are tricks to reduce that quite significantly. Then there is a thing about using a different CP on the different side, dynamics and physics. That's about 0.5 watts per meter squared. Then there's a part I didn't talk about at all, but it has to do how water enters and leaves the atmosphere. So energetically, we do not close that budget. So as soon as a permeation decides that falling precipitation is formed, it just goes straight to the surface and it doesn't interact with anything. It just falls to the ground immediately. So if you were to walk around in CAM and it rains, there'll be water there, but you wouldn't be hit by any water. It just, and the energy associated with that, we're not rigorous about. So that's this enthalpy thing here. It can be pretty large, 1 watt per meter squared-ish. Kinetic energies, potential energies associated with all these hydrometeors and whatnot is really tiny. I wouldn't worry about it. And the same with all forms of water and pressure and mass, really small. And then there's the thermodynamic inconsistencies between permeation that I just showed, which can be rather large. So a lot of junk in there, and we just throw it all into an energy fixer and fixes it. So I hope I convinced you that this is a can of worms. As model developers, we do work in codes. We don't have any fear of coding in big systems, but we do need to think about these things. And especially if you want to do physics dynamics coupling research, because it's really, really hard in legacy systems. So it's hard to change the scheme order because they're interconnected. You have to unwrap a big spider web to change the order. Adam can attest to that. It took him like 6 months to move the call for a club from before the coupler to after the coupler. It's very hard to look into higher order coupling because if you want to do Runge-Kutta, you have to run like a third of the time step, then run physics, and then come back and whatnot. There's the thermodynamic consistency issues where you really have to go into each permutation, figure out what assumptions it's making, and hope it would be nice to take them out of them. And then, as I just mentioned an example, it's really dangerous to carry temperature tendencies around because you don't know under what assumptions they were at, like constant height, constant volume, condensates, no condensates, blah, blah, blah. But there is some hope out there. We're working with NOAA and NRL and just trying to define interfaces for parameterization, so it's going to be easier to move them around. It's called the CCPP. But there's definitely a lot of more work to be done in that area. Okay, last but not least, Adam stole these figures from my presentation, so now I'm stealing them back. Remember he showed this? You know, this shows the grid resolution, and he made a big point about that's not the same as the effective resolution. Cristiano showed it too. So that's, you know, you see, we're not representing the shortest scale. We're damping them too much, and they may propagate with the wrong phase speed. So University of Reading with Landon Hoskins back in '97 proposed that, well, no, why should we send stuff we know is not well represented in the model to physics? And I kind of picked up on that together with Adam, and Dewey was involved as well. So we tried to do this in the spectral element dicore. And as with anything, it sounds much easier than it is. So what we did there, which I think also UK Met Office is doing, is we're separating the dynamics grid from the physics, or from the transport grid. So in the case of spectral element here at NCAR, we have the CSLAM transport grid there. GLL grid is our dynamics grid. And then we have the option to run physics on this equiangular, more or less equal area grid, the PG3, same number of degrees of freedom, apart from 2 points, I think, globally to the GLL grid. And then we have a coarser physics grid or a finer physics grid. So the coarser physics grid follows this idea that we're chopping off some scales we know we're not representing well, but we're not chopping off enough here, because for like a 1 degree model, this is 1.5 degree models, like we're barely chopping the 2 delta x wave, but at least you're getting rid of some of it, I'm pretty sure. So that option we implemented. The other thing is I only have 4 physics cells in each element here, whereas in this example up here, remember the points on the edges are duplicated, so there's really only 9 independent points there. So we go from 9 physics columns to 2 physics columns, so that's more or less a 2x speed up of physics. We proposed that in CAM, but people are not quite ready for that, but E3SM DOE has done this, and it makes Brian Dobbins very happy, because physics takes up a lot less memory when you have half as many columns. So we looked into that. I didn't have time to add Adam's figures, but we basically showed, we used high order mapping to go between these grids, and we showed in terms of energy spectra that we actually didn't lose any variability for the full model with the half resolution physics grid. So I didn't have time to add that, but that's in the paper. So that's another aspect of physics dynamics coupling. You can separate the grids. I also want to mention that some people argue you should do this. So like the subcolumn idea in physics is you should sample physics with slightly perturbed states to get a better statistics of what's going on subgrid scale. And you would somewhat naturally get that from this grid, but now I made physics about twice as expensive, which is unpopular. So there's some debate, what's the optimal approach here. Okay, last but not least, I just want to highlight that if you're interested in physics dynamics coupling, there's a relatively new conference series. So if you go into the literature, you will find Dicor papers way back. You will find parameterization papers that go way back, where you won't see that many papers on physics dynamics coupling. So this is my favorite conference. Started back in 2014, we went to Mexico there, and then Eastern WF, PNNL. Was it Oxford or Cambridge last? I don't remember. Exeter, there you go. And GFDL, yeah. So if you're interested in that kind of stuff, that there is this conference series that kind of highlighted to the community, this is actually important to think about. This is not a detail that you just leave for somebody to implement. It's actually, there's a lot of science that goes into it. So with that, I will take questions. All right. Yes.
So, I mean, with your last comment about the, people are now focusing on the advancing the science of physics dynamics coupling. Do you think there's hope of coupling approaches that are better than Peter Caldwell's provocative first order statement?
Yeah, you can. Well, I don't know. But we have not explored higher order coupling. But, do you need to do that on all of physics? Like, radiation is usually it's on much longer time scales than like microphysics or deep convection. So I would be really excited about trying out higher order coupling for really fast processes, so that the Dicor is more in sync in what's going on with the fast processes being represented in physics. And I think there has been some work, like FE3 moved some microphysics into the Dicor, or MPAS has Neptune.
Or UKMIP.
UKMIP physics. And then also MPAS, sorry, is also running microphysics at the end of dynamics. But that's not high order coupling, it's just running it there, but then, so that's that's what I would do. And at that, as a community, we haven't explored too much in that direction. Yeah.
So you might have been getting at this towards the end, but is it additional source of uncertainty, the lack of scale awareness in some of these parameterizations, meaning some of the tendencies, you know, if they're not scale aware, then they increase the leaking?
If there was a Nobel Prize for model development, gosh, is it this far back? I think one of the grand challenges we're facing as a community is this situation here. So some parameterizations, like anything to do with topography, we pass like subscale variance and whatnot from topography to the grid. But that one will immediately adapt to the cell size. The subscale variability in a small cell will adapt naturally. But then there's like a deep convection. So there's like the Graf-Freitas scheme is one where they try to gradually shut it off if you get into this. But one problem with deep convection is that all the assumptions that are made in there is that the plumes only take up a very small part of the grid cell. So that's like 100, 200 kilometers. So what should happen when you get to 25, where you're like not really resolving updrafts, but slowly getting there? What should the convection scheme do? So there's a huge amount of challenges with that. On the die-core side, I think the problem is solved. The viscosity operators, etc., really adapt to this. We're not seeing any weird behavior near the boundaries as you do in regional models, where like I used to work at the Danish Met Office running regional models, and you don't want to look at precipitation. It was like a line of precipitation right at the boundary. So you have this high level of consistency and variable resolution, which makes it very attractive, but parameterizations is a problem. Because we tune our parameterization for like the 1 degree. The tuning would be different for 1/4 degree. How do you get between all that? So, yeah. Alrighty. Yeah.
I actually worked on the physics dynamics coupling for one of the DCMIP test cases at home with Mark for a summer. And I want to echo how annoying it is that these parameterizations don't tend to readily admit the assumptions that they make. So the implementation that we saw was supposed to be isobaric of Kessler microphysics, yet it updated the pressure in the implementation. They weren't quite sure why. So we got rid of the pressure updates and saw different results.
Yeah.
Especially for the 2016 tropical cyclone test case. So I just want to echo your sentiment.
Well, that was one of the reasons I went to dry mass vertical coordinate in the die-core. I'm a little less convinced now that it's a good idea, but what I really wanted, it was kind of to, what I really wanted, I want a coordinate that doesn't move when you have evaporation and precipitation. So with moist pressure, coordinates it moves up and down, but the dry pressure stays constant.
Right.
When it is constant, then it's more explicit, everything that happens. If we had that in physics, I think it would be easier to enforce a little more consistency. To not have a variable coordinate that moves up and down. So CAM physics will assume constant moist mass or pressure, hydrostatic, throughout the integration, even if water rains out or comes into the system. And then at the very end, we then adjust it. The energy tendency associated with that, we just throw into the mixer because we don't know better, or we haven't implemented something better.
Right.
And it's not easy to implement something better. I'm trying.
We're rooting for you.
Yeah. Mark.
Following Jason's question, Kessler physics in particular, do you know what assumption it's making internally when it returns a temperature tendency?
No, I have to look at it. I don't know.
So we had trouble determining that, right?
Yeah, we found constant pressure for it. We have a report out in Google, our name, and physics dynamics coupling.
Oh, cool.
There's some pretty figures of the tropical cyclone test case.
Hey, I think the refreshments are out
Right, they will be near the library again.
near the library again.
Yep.
Okay.
Are we still
Then,
shelter in place?
then we're gonna come back here and
I checked the-
Mark is gonna talk.
Yeah.
Are you gonna do both? Or?
Yeah, let's have a break until, 3:45-ish or so. Come back here and then Mark Taylor will present, I don't know, one talk? One or two? We see. So Mark is on the agenda tomorrow for 2 talks, which are half an hour each. So we will see whether he wants to present 1 or 2.
Mark just gonna go as long as too loud.
There was a shelter in place. I'm not certain whether it's lifted. We maybe want to watch the situation.
Or I think they just pulled the guy out.
Colin.
Safe.
He's not listening. Okay. Colin. By the end of this, you will be transparent. Hey, thanks everybody again for your understanding here. It's a very long day of lectures, but that's how it is.
Yeah, we're thriving.
Yeah.
You're doing great.
None of you fell asleep during my talk, so you're doing really well. All right, so
I'll
Mark,
work on that.
yeah. As you know, Mark has been involved in DCMIP since the very beginning. I think it's appropriate to say without him there wouldn't be a spectral element, various versions of the spectral element, dicore. So he's definitely my guru whenever I have dicore issues. So take it over.
Thanks, Peter. So I'm going to give an overview of the spectral element method. I'm going to start with kind of a repeat of Christian's talk about grids and stuff, and mention the decisions we made in developing the spectral element method. And I want to really focus on 2 key principles that haven't been mentioned too much, but that I'm really interested in, which is Hamiltonian structure preservation and entropy stability. And then I should have had a description of Galerkin methods and the spectral element method, and even the closely related and also these days getting more popular discontinuous Galerkin methods. But I don't have slides on that, and I won't, in my 30 minutes, I won't get to that anyhow. But there's great textbooks on that, for that material. So it's just an overview of some of the acronyms. You may have heard this acronym mentioned, HOME, High Order Method Modeling Environment. That's the software package in which the spectral element method that we're using in this workshop comes from. It's a standalone model that supports a suite of continuous Galerkin, or otherwise spectral element methods, as well as discontinuous Galerkin dynamical cores, both 2D for shallow water and 3D, hydrostatic and non-hydrostatic. It was originally developed at NCAR. The hydrostatic continuous Galerkin version is used in CAM SE, and the first 2 tests in DCMIP 2025. NCAR dropped support for a standalone home as its own model, but we still maintain that in E3SM. So it is possible to get the home dicore by itself and run that. The non-hydrostatic version of the spectral element method was originally developed for this method within E3SM, a different project that funds a lot of us in DOE for the SCREAM model, and it's been incorporated into CAM and used by the Storm Speed project, and that version is used in the 3rd test case. So there's a little bit of complication there with the slightly different versions of the models. So starting with a computational mesh, this is I think we've seen this slide at least every day. The spectral element method is on the cube sphere. See if I can, is on the equiangle cube sphere. The spectral element method itself can run on any quadrilateral mesh. It doesn't have to be a cube sphere. So if you can come up with a better way to tile the sphere with quadrilaterals, they have to be quadrilaterals, that will run as well. The cube sphere is one of the most quasi-uniform versions, and so we usually start with that. And let me go back one. In this transition back in the 2000s from latitude longitude grids to these icosahedral and cube sphere and yin yang grids, one of the advantages of going to finite elements at that time is that you can run not only on the cube sphere grid, but on the really arbitrarily unstructured mesh grids. So they're not tied to the cube sphere, and then you can run mesh refinement. And in the spectral element dynamical core, we only have really played with static refinement and only in the horizontal direction. So this is just an example of the unstructured mesh relatively smoothly transitioning from low res to high res over CONUS, continental US. There's a lot of work in adaptive mesh refinement that came up, I think, on the first day. But the home model used here doesn't support that. Vertical coordinates, we saw a nice talk this morning from Dave Randall on this. I'll just say in home, we also went with the terrain following that he discussed a lot. But just to mention some of the options. So terrain following is where the coordinate lines follow the topography, so they don't intersect the topography. That's what I meant by no lateral boundaries to worry about. But as Dave mentioned, the results with realistic topography, so you can imagine steep mountains, very distorted coordinate lines, can be noisy and poor. Another alternatives, this is the kind of the crudest, which is not really used, where you just have a stair-step topography. So you have your mesh and you just eliminate cells and replace the topography with these stair steps, which doesn't work that well. Cut cells, it's easier if I look here. I think cut cells is you cut the cells and you get really good, these methods have really good treatment of topography, but they introduce a new challenge, which is you have the really small cells and you have to worry about CFL conditions and how to handle those funny shapes. But the spectral element method is terrain following mass or pressure coordinate. Another issue that it hasn't really been called out explicitly, but I'll describe it here on this slide. Once you have a grid like this, you can say, how are we going to discretize it? You can take if you have a 3D code, like an engineering code, I guess somebody did mention that. Why don't we use in this field the same 3D Navier-Stokes codes used by like various industries and other fields? And it has been tried. You take a good 3D unstructured grid code and you run it in these problems, and it usually doesn't do very well. I think there's two key reasons. Dave mentioned that the dissipation is very anisotropic. You need a lot more dissipation along the surfaces than you do vertically, and that's related to the aspect ratio. So in the climate model with 100-kilometer horizontal spacing and 10-meter spacing at the 10-meter spacing at the surface, you have a huge, very thin cells. And there were some nice pictures of the thinness of that in several of the talks. So most models use what I call a 2D plus 1D approach. You write your differential operators along these eta surfaces. So I'm calling them eta. Dave called them sigma this morning. And you have a horizontal discretization along these surfaces. So now you need 2D differential operators on these curvilinear manifolds or surfaces. And then in the vertical, in home we use simple finite difference methods. So here are the equations in a form very similar to various forms that we've seen used in various models, starting with the original Euler equations in Cartesian coordinates written in this terrain following coordinate system, where I have differential operators on eta surfaces with the subscript eta, and then vertical, so this is split into those horizontal or eta surface operators and then vertical operators with the dd eta derivatives. What was I going to say about that? Oh, and so the operators are, just to mention, and I forget which talk I think also Dave's talk, these operators, div, the only thing that appears here are div, grad, and curl on manifolds, and they're so-called coordinate-free operators. They're defined on any manifold, independent of any coordinate system, and well-defined as basically surface integrals. And we use this form because we avoid the more complicated non-coordinate-free operators like gradients of vectors, which lead to tensors. And the velocity, similar to, I think also Dave this morning, split the velocity, but a different notation. U is horizontal velocity, W is vertical velocity. And so what I'm going to go through is how we get to the type of equations, the decisions we made to end up with the equations that we're solving. And the first condition is linear geostrophic balance. So the atmosphere and the large scales are in near geostrophic balance. Linear balance is a particular idealized form of that. If you look at the linearized shallow water equations, and with a constant Coriolis force, there's a steady geostrophic mode, a family of steady geostrophic modes that don't propagate. And a numerical, we'd like to, that's an important mode. It carries a lot of energy in the atmosphere, so we'd like the numerical methods to do as a perfect a job on that very simple mode as possible. And so in this very simplified system, if you discretize, if you put in this mode, you want it to be stationary, to not move, and that if it does move, it's generating, it's basically spurious sources of vorticity. And an easy way to do that, not the only way, but one of the easiest ways to do that is to use a vector invariant form of the momentum equation. And here I've written it for the shallow water on the left. And then to get this property, you need your discretization for gradient here and curl, which is used to define the vorticity, has to have this property curl grad equals 0. So the discrete curl applied to the discrete gradient should be 0. And then you'll get this property. So that's two conditions we look for. We're going to put our equations in, we're going to put the momentum equation in this particular form, rotational form, not conservation form. And we're going to demand of our numerical method that our div and grad have that property. So I put in red, that's that equation. I'm going to go through them one by one. The rest is going to be based on conservation. And Tuburn has a really nice paper surveying conservation issues for atmospheric models. There's an infinite number of conserved quantities, and we can only conserve a finite number in our models. And he kind of goes through all the important ones, discusses each in great length, and categorizes them in different categories. In particular, there's robust and non-robust. And that means the robust conserved quantities, that's this issue between the Euler equations and the Navier-Stokes equations, or the adiabatic reversible system. And then we add dissipation or other non-reversible effects. So if it's conserved in both systems, it's robust. A lot of things are only conserved in the Euler equations and not when you add dissipation, and those are non-robust. And then there's, if they have a cascade, and that's usually because we truncate the scales, does the conserved quantity cascade down to smaller scales or not? And so the mass is one of the most important things to conserve in these models because it's robust, there's no cascade, and then the last column, there's the time scale at which the sources and sinks change the conserved quantity. So if the time scale is very short, there's large sources and sinks, and maybe you don't have to pay too much attention to conservation because it's going to be changing dramatically throughout your model. So mass is infinite, mass is absolutely conserved at all scales and very robust, and so it's basically a requirement. Momentum has really strong, so technically conserved, and to conserve momentum, you'd need to write your momentum equation in conservation form, which we're not doing. But the time scale is minutes to hours, so it's one of the conserve quantities with the largest amount of sources and sinks, and in home we make no effort to conserve that. Two that I'm going to end up talking about, or I'll mention one that Chuburn points out is quite important is unavailable energy. Robust quantity with no cascade, relatively long time scale. We should really conserve that. It's very difficult to do that, and I think maybe one of the only ways is to use these theta coordinates that Dave Randall talked about. So we don't do that, and I don't know of any full 3D models that do that. The ones I'm going to talk about are entropy, which is almost robust and no cascade, and but many different time scales. Energy, total energy, which is the sum of available and unavailable. And then tracer variance, but actually entropy variance. So tracer variance does have is not robust and does have a cascade. And Peter, give me a 25-minute warning, because I didn't go through this. I actually don't know how long this presentation is, so let me know 25. Okay, I'll take anything I go over, I'll take out of my talk tomorrow. So mass conservation, we've talked about that. You put it in conservation form, write it as a flux, or divergence of a quantity, which is equivalent to a flux. Everything I'm going to talk about is global conservation, but everything I say in the spectral element method also applies locally. It just brings in flux boundary terms and makes everything more complicated. So I'm just going to, for simplicity, only talk about global conservation. So that the conservation of mass determines this equation here. The next thing I'm going to talk about is entropy stable methods, and these are choosing entropy and total energy as conserved quantities, but mostly motivated by stability, not physical concerns. I mean, they're good. They're very clearly very good to conserve, but entropy stable methods by design are designed to make your numerical method very stable. So an entropy stable method is a method that conserves both total energy and mathematical entropy variance. And I say, I'm going to use the word entropy, but what I really mean is potential temperature. And in our system, the physical entropy of our system is the log of potential temperature. But I'm going to adopt this terminology from the literature, and I'm using, applied to, so when I say entropy, I mean potential temperature. And so you conserve entropy, which was desirable, and our adiabatic core, before we add dissipation, we conserve entropy variance, or potential temperature variance. And then you add dissipation. So Christiana talked quite a bit about this. Spectral element method is the philosophy where the adiabatic core has almost no dissipation, and then all the dissipation is added afterwards. And I'm just talking about that adiabatic part. You then want to add dissipation in a way that respects the second law of thermodynamics, which means entropy should increase, and entropy variance should, you should remove oscillations from your entropy variance. Here's the energy and entropy. So two ways common in the literature for entropy stable methods. One is, in our equations, we have a thermodynamic equation, which can either be potential temperature, or energy. And so one way to work on this is you write that equation for total energy in conservation form, so you're guaranteed to conserve energy. And then you have to, with a bunch of algebraic manipulations, back out your entropy from your model and see what the model is doing to entropy, see if it happens to be conserved, and see if you can also conserve both entropy, and I'm using theta for potential temperature, but entropy and entropy squared, or potential temperature variance. The approach Home takes is we write the equation for potential temperature in conservation form, so we get that for free, and then we need to conserve total energy, and we do that by preserving the Hamiltonian structure of the equations. So here's our entropy or potential temperature equation written in conservation form, so that's conserved. And then we go to trying to conserve energy. Let me go back to, where did I write that? Here is the energy of the system. So we don't have prognostic variables for these. We have to solve for the various variables, compute this quantity, and see if it's conserved. And this Hamiltonian approach was really pioneered by Salmon. To this paper, I really like this quote from this 2004 paper. So he's talking about conservation laws in general, but he says, from the standpoint of differential equations, conservation laws arise from manipulations that typically include the product rule for derivatives. Unfortunately, the product rule does not generally carry over to discrete systems. Try as we might, we will never get digital computers to respect it. And so here's the derivative product rule for our horizontal operator on manifold. Divergence of rho u should be rho divergence of u plus u divergence of rho. And if you compute this in a pointwise in a numerical method, I think you would be surprised how poorly, you can have very good derivatives, but how poorly this equation holds. And Salmon's idea, he noted that, so it's impossible to get a derivative product rule, but we can get the integral of the derivative product rule, or the so-called integration by parts rule. So if you just integrate that equation, integral, and again, looking at global conservation, if you do local, you have to put in the boundary term, replace this by the boundary integral. But if we just do global, this will be 0, and we have that these two sum to 0, and that's classic integration by parts. And the discrete version of that, if your numerical method respects this property, is called summation by parts, SBP. So I'm going to talk about SBP methods next. So if you write, and then Hamiltonian form comes in, if you write your equations in Hamiltonian form and you discretize with an SBP numerical methods, this will actually guarantee conservation of the Hamiltonian, which is the energy. It's not exact conservation to machine precision like mass or entropy. It's semi-discrete. So it's up to, it would be exact if your time-stepping method was exact. So in this approach, we don't have exact time stepping, and there will be some dissipation from the time stepping scheme, but we still call it energy conserving. And this, doing this in full models, I think the first ones I'm aware of is Dubose and Tort, starting in 2014. And just a quick, I'm not going to talk about the Hamiltonian formulation, but I just want to say what it means is you write your energy, and you call that the Hamiltonian. You have to know what this functional derivative of an integral is, and the functional derivative gives you other functions. And you write your system of equations as dx dt, which acts as a vector of all your knowns, is equal to this Jacobian matrix times the functional gradient of the Hamiltonian. And the Hamiltonian formulation means J is skew symmetric. So if J is skew symmetric as a differential operator, it's now a matrix of differential operators, but if it's skew symmetric, it has all these nice properties, just like skew symmetric matrices. You dot this system with H, it's skew symmetric, energy conservation falls out for free. And it's a little more than just energy conservation. You can also say you're preserving you're preserving the Hamiltonian structure discretely. So your discrete system is discretely Hamiltonian. So the Hamiltonian condition determines the rest of these equations. These equations give you like half the system. Then if you write everything out in terms of differential operators, the fact that the equations have this adjoint property means the operators that appear here have to be adjoints of the ones that appear here. And those adjoints are why the integration by parts property is important. So that determines the final form of our equations. Am I over, Peter? You're not checking the time, so I'm just going to keep going. Okay, I'm almost done. So to get this property, which we've worked hard in the spectral element for, you need two things: summation by parts and curl grad equals 0. And these methods are sometimes called mimetic because they mimic the discrete operators. There are also some methods that have these properties are sometimes called a discrete exterior calculus because they actually, if you define a calculus instead of the continuum calculus that we're used to, but you define a discrete calculus, you'll get this class of operators. And the right way to study this is probably this discrete exterior calculation, differential forms, and things like that, which I don't understand, so I just wanted to put this slide up to recommend that to you. And an important property is that this family of operators form what's called a de Rham complex. So you might hear that. If you don't already are familiar with this theory, you might hear that. So some examples of mimetic methods. It actually came up this morning: Trisk, Tuber, Ringler, Skamrock, and Klemp. That's a mimetic method. That's an impasse. And I think there was a question about this morning, but so Trisk is a truly mimetic method, but I think the final implementation in impasse is not, they've made some changes for various reasons. So it's not a true, the purists would say it's not a true Trisk method. But Trisk is a mimetic method, and it's explicit. Pete talked about time-stepping methods that are implicit or explicit. So Trisk, if you discretize with Trisk, your system stays explicit. The one possible disadvantage of Trisk is it loses second-order accuracy on spherical grids. So there's some aspects of it that drop to first or zeroth order accuracy on spherical grids. The UKMO has a mixed finite element method or finite element exterior calculus method. That's a full mimetic method, and maybe we'll hear in the next talk, but I think the Elfrich model will preserve all these properties. It retains its order of accuracy, second order, if not higher, on spherical grids, but it has a disadvantage that it's not explicit. It leads to an implicit part in your time step. And then the value in spectral elements is a explicit method. It retains its order of accuracy on unstructured grids, and it's basically an A grid. We heard about that too. A grid collocated method, which makes it easy to go to high order. So it's typically run at fourth order, but it's not truly mimetic. It has this A grid property that there's a 2 delta x null space, so that results in a 2 delta x mode that's stationary and looks quite ugly. And because it's stationary, it stays there and imprints your grid on the solution. And so we have to make sure to damp that when we add our dissipation. I use this term entropy stable methods. They had 3 properties: energy, entropy, and entropy variance. And the version of SE doesn't actually conserve entropy variance. This is some really new work that's, I think, quite beneficial, and we just started playing with this. It hasn't made it into the versions we're using here of Ricardo, Lee, and Juru. Still not even published, but it's in the archive. They showed for DG methods how to make them, which are quite similar to spectral element methods, how to make them entropy stable by following the same procedure I outlined, but then replacing the entropy equation with what's called split form. And you can see this is related to the product rule. This is the divergence term, and this is the divergence term expanded out, and they should be the same, but they're not because we don't have a product rule. And split form just averages them. And then through a little algebra, you can show entropy stability. You get conservation of variance that we're then eventually going to dissipate by adding dissipation. And it makes the model much more stable than it has been in the past. So far, with this small change, we've been able to run most test cases with no hyperviscosity at all, but they are noisy. And okay, so just in summary, the spectral dynamical core, terrain following, unstructured quadrilateral grid with a mimetic summation by parts method. I didn't talk about the vertical. Spectral elements is only used in the horizontal. The vertical is this one that we heard about this morning, Simmons and Burge, finite difference. That scheme actually does have a product rule because you can get product rules, derivative product rules in one dimension. Hamiltonian structure preserving. Everything I talked about is this adiabatic or reversible dynamical, the core of the dynamical core, which has almost no dissipation, and we add dissipation in the many complex ways that Christiana talked about. Thank you. I'll stop here.
This is a philosophical question. So your first bullet up there actually gets to the point. You're very differently. Huge amount of sophistication and horizontal. But this seems fairly common in a lot of models that relatively low order schemes are used for vertical. I'm curious, just philosophically, do you have an opinion on why that is? And are people exploring higher order methods for the vertical?
Well, I like Dave Randall's talk this morning when he said simple is better. And so in the vertical, so I think we were first motivated by spectral elements in the horizontal because the sphere makes it difficult. The structured methods have problems, and spectral elements is a way to handle the unstructuredness. In the vertical, it's one, it's a simple 1D domain, and the Simmons and Burge finite difference is actually a mimetic. It's not only mimetic, but it has a derivative product rule, which is very rare, and I think should be exploited if we don't need fancy, maybe people will want vertical variable adaptivity in the vertical, things like that, and then you need new class of methods. But so that would be my philosophy on that.
Thanks.
Yeah.
Sorry for a basic question, but why, is there an intuitive reason why computers don't have the derivative, or why they don't have the product rule? Are the errors just small, but that small error is still not conserving, or are the error, using the errors?
That's a good question, and Salmon is the one who really spelled it out explicitly, and he doesn't explain why it's hard. So it's actually a great question, and I don't know the answer to it. So the C grid in a perfect quads, it does have a derivative product rule, but it's only special cases, and if you change anything, you lose that property. Maybe someone else in the room knows why it's hard, but yeah, I don't. I'll take a guess. It's probably so like spectral elements is differentiating polynomials of degree 4, but then you do a product that's now of degree 8 because you multiply them together. Mm-hmm. So your method is designed for degree 4, and it doesn't work very well on degree 8 polynomials.
I don't know. Something?
I have two, I guess. First, how do you bring in moisture? Are you doing virtual potential temperature? That's one. And I couldn't recall your total energy. Does it have a moisture contribution, or how do you deal with that?
So I didn't talk about that. So here it's just dry. We use in our system what's called the constant kappa approximation. So we like that because you define virtual, so we use virtual potential temperature, but with a kappa that's constant. We don't let kappa depend on moisture, which it sometimes does. And we do a constant kappa approximation consistent in the sense that Peter mentioned, that it comes from a Gibbs, the approximation comes from a Gibbs potential. And so this energy, that has the advantage that it decouples the water vapor, the water species transport from the dynamics. It doesn't appear in the dynamics. So that's nice for running tracers with a different scheme than the dynamics. But it does force us to use a full pressure, a water-loaded pressure, not a dry pressure.
That's why I mentioned I'm not completely sure dry pressure is the most efficient way to do things
Unfortunately,
in the
Dave
dipole.
Randall is not here now. Because he said he really likes dry pressure.
Yeah, no, I would like if physics had dry pressure, that would be nice. So the coordinate surfaces don't move. Okay, let's give Mark a hand again. Okay, you can do it, one more. So, Thomas, I think you volunteered. Do your talk.
Is there
Okay.
a click?
Ready. So you hold this in, and then it will show up. There's a little delay. So.
Okay.
Okay, so we're very excited to have Thomas Bendall here from the UK Met Office, and he's going to talk about the latest and greatest from ELFRIC, which is the UK Met Office new DICOR, and is it also physics or is it just DICOR?
Well, next slide. Yeah.
Oh, okay.
Yeah.
Take it away.
Yeah, thank you very much. Thank you. So
I'm really excited to be here. I was quite sad when the last one got cancelled because of COVID, and I was just a bit too young to come to 2016, so thank you for allowing me to come. So today I'm going to talk about the Met Office's new dynamical core, and to start off with, what do I mean by a new dynamical core? So our current model is called the unified model. So I realized, like Mark, I'm starting with a whole bunch of acronyms. So I'll always call that the UM. And that's now quite an old model. We've been using it since 1990. But it's used for lots of different applications: climate, global NWP, and regional forecasting. And the dynamical core at its heart is called Endgame, and this uses a latitude-longitude grid for the global model. And so we're replacing this with something called ELFRIC, and this is named after Lewis Fry Richardson, who we heard this morning from Pete. Almost the last acronym for now, Gung-Ho is the name of the dynamical core. So Gung-Ho is the replacement to Endgame, while ELFRIC is the replacement to the UM, kind of. Because we've got a new modeling framework, which is called Momentum, which isn't an acronym, but it could be. Well, we've kind of backronymed it slightly, Met Office as MO and as UM at the end. Anyway, so the talk is, how have we chosen to design ELFRIC? And something that I should say is this isn't yet operational, so the plan is for about 2 years' time this will be operational. Okay, so brief outline. It's kind of like Mark's talk, actually. What principles have we used to design this dynamical core? And I'll talk about those and then go through what that means for the design of the model, and then put a particular bit of focus on the transport schemes. Okay, so why are we building a new model? This has been kind of mentioned in many talks earlier this week, but the latitude-longitude mesh used by Endgame has all of these points that are clustered at the poles, and for the 10-kilometer global resolution that we run every 6 hours now, the horizontal spacing of points at the pole can be 12 meters. So that's like, 2 points for this room or something. And so if you get fast winds at those points, we take time steps of 4 minutes. That gives completely ridiculous current numbers, like you're circling the pole multiple times in a time step. So we have a whole bunch of fixes to avoid that happening. But not only is it unphysical, if we try and go to even finer resolutions, it's going to be more of a problem. And whatever you do, you're going to have very big parallel data communication costs. So this is a really old plot that I've stolen from Nigel Wood, who used to be head of the dynamics research team that I'm in. So it's a bit of a funny plot. On the y-axis here, we've got time. And then this is number of nodes, and I assume power 7 nodes is some kind of ancient technology. So this was like a state-of-the-art great plot when it was shown, because so new dynamics is the model before endgame in the Met Office, and this was showing endgame is scaling much better than new dynamics was. But you see that you've got this kind of plateau here. We're adding more and more processors, but we're not getting the speed up that you'd expect. And there's other plots like this you'll see with scalability. And so the idea is, can we improve on this by having a quasi-uniform mesh? And I think probably all the things that I said on this slide are what I've just said. So back in 2011, which is a long time ago now, the endgame wasn't yet operational, but it was fairly clear that there was going to be this plateau and that we would need to replace it in order to exploit the next generation of supercomputers, which have now arrived. And we're turning off our current supercomputer in 2 weeks' time and moving over to the new supercomputer. So this is very live for us, exploiting this new, more powerful generation of supercomputers. So that is what has motivated this new grid, and this leads me to start a whole bunch of lists. So I hope you like lists. And I thought you might, it might be a bit more memorable if I use some really old word art here. So there's going to be a whole bunch of principles, and so our first guiding principle with how we're going to design our new dynamical core is it's got to be quasi-uniform. And the spoiler is here, we ended up going with the cube sphere. Yeah. So there was a thing called the Gung Ho project, which was a whole bunch of funding for research in the UK, which went from 2011 to 2016, to try and work out how we were going to design the discretization for this new model. And that's what I then go on to talk about. So now I have a brief interlude before I get to the other principles, which are like 3 even more fundamental things for just modeling in general, which are, I've called them ABC. These are like the 3 really, really important things. And the first thing is stability, because your model can't crash. When it's been run operationally, the people who are actually executing it will yell at you if it crashes. And the second thing is we have contracts with lots of customers, and they will yell at us if the forecast doesn't get executed within the 1-hour window that we have. And then finally, and only thirdly, when you have the other 2 things, is accuracy. And everyone will yell at you if it's not accurate. So these are kind of 3 things that you have to get on top of if you don't want to be yelled at. Okay, next principle is seamlessness, which I think is something that's not widely done, but it's a principle for us, which is the idea that the same model works for all of the different scales that we want to do, so regional, NWP, climate, and we're going to have the same code base that does all of these things, and the same dynamical core, the same physics package, with only a few adjustments between them. And this is what led to the unified model approach. So we've been doing this for quite a long time. And part of the reason for that is just to build trust. Like it's the same, you're more confident in your weather model if it represents the climate accurately, and you're going to be more confident in your climate if it represents the weather accurately. But there's also a practical point of view, which it means that we don't have 3 separate teams working on 3 different models. We've just got one team building one dynamical core. Okay, so even though the model is called Gung Ho, the Met Office is quite a small c conservative organization. And so this slide, this slide ends with the principle, and I'm just going to say what the principle is. The principle is we don't want to change very much, even though we're changing a lot. And the reason for this is that the Met Office is actually, oh, this sounds like bragging, but we're quite good at weather forecasting. So do be cynical about this plot. This is an internal Met Office plot, but it's basically a score of a whole bunch of different global Met services, and they all send their forecast or data to the WMO, who kind of collate it and then verify it. And the reason to be cynical is that this is a Met Office internal score system, but on this score system, we're doing quite well. Only ECMWF consistently have a better score than the Met Office. But what this means is that people are very reluctant to make radical changes because we're quite happy with how we're doing so far. And we have quite a lot of partners, so you can see up here, the Bureau of Meteorology in Australia, they use our dynamical core. So when we make a change, that's going to impact lots of people around the world who run our models. So yes, so the principle here that we have is that we want to keep as much the same as possible when we're changing the grid and changing other things. Okay, so this is something that's kind of been touched on. It's a little bit different to what Mark said, but a few talks have mentioned this. I think Owen said that we have a Bible, and what you're about to see is our Bible. A paper that's been really influential for us that kind of was connected with the Gung Ho project was by Andrew Staniforth and John Thuburn, who listed a bunch of properties that they said were really desirable for dynamical cores to have. And I'll kind of leave you to read those, but the thing that I want to highlight in particular, these bolded and italics ones relate to kind of wave modes and dispersion properties. And so that had a lot of attention in the design of our dynamical core. So Endgame doesn't have all of those 10 properties. It has, can I count, 7 of them. And these were things that we didn't want to lose. We wanted to keep all of these properties in the new design and maybe add some more as well. So property 4, good wave properties, which come from these kind of bolded and italics ones. And then I'll move swiftly to property 5, which was the one thing that Endgame didn't have, was local mass conservation. There's a global mass fixer, but no local mass conservation. And when we were designing Gung Ho, there was a survey of lots of the users of the unified model. And their, by far, top request was that we add local mass conservation. And this is actually slightly controversial whether it's necessary, but part of this comes from the seamlessness approach. So climate modelers don't really like to think that carbon dioxide or moisture, that a source or sink of those chemicals is the transport scheme in the model, because they put so much effort into trying to measure the budgets of those. So this was something then that came to be our final principle in designing the dynamical core. Okay, that was our 5 principles. So seamlessness, it has to work across all scales. Quasi-uniform, I've swapped those 2 around, oh well. Change as little as possible, good wave dispersion properties, and local mass conservation. Okay, so taking these principles has then led to the design of our model. And the first 2 that I want to talk about are, I switched them around in order, but anyway, good wave properties and the quasi-uniform grid. How are we going to achieve those 2 things together? We've seen the different horizontal staggerings. This is another illustration of those. And a simulation, I think this is a shallow water model that's been kind of pinged with a little perturbation and then watching the waves ripple out with a bunch of different grid staggerings. And you can see that different grid staggerings give rise to different kind of computational modes. That the unified model uses the C grid. So this kind of still fits under our don't change these things, but managing to replicate these properties was then high up on the list of things that we wanted to do. And the way that we do this is something called compatible finite element methods. And this is quite similar to what Mark talked about with spectral element methods. And the idea came from a paper by Colin Cotter and James Shipton, who were my PhD supervisors. They showed that this kind of method can replicate many of those properties that we saw that Andrew Staniforth and John Thuburn listed. So in this type of method, you've got finite elements where you are expanding your field as a series of polynomials in cells. That's appealing because they're good at handling non-orthogonal grids, so that will help us get to the quasi-uniform grid. But the principal thing of this compatible method, as opposed to the spectral element method, is that we use different basis functions for different variables. So the prognostic variables end up lying in different spaces, and this allows us to mimic lots of the properties of the underlying equations and the C-grid staggering. And I'll just briefly say that then these function spaces form a de Rham complex, and lots of the nice properties stem from us being able to replicate at a discrete level these vector calculus identities. So the type of finite elements that we use we call lowest order, and what that means is that the density and pressure fields are just constant within a cell. And part of the reason for doing this is change as little as possible. Our grid, our kind of laying out and staggering of variables then matches what we use in the UM. And I didn't mention this, but the UM also uses the Charney-Phillips grid for the same reasons of the nice dispersion properties. And then finally, we were talking about vertical coordinates today. So our cells are like 3D volumes that are terrain following. And so we kind of use a height-based vertical coordinate rather than a pressure one. Okay, what are we keeping the same? As I said, this is very important for all of our partners. The physics schemes are staying the same, so they've just been ported from the unified model to ELFRIC. The equation set is still non-hydrostatic, and we don't yet include deep gravity, but we do have a deep atmosphere in that our columns get wider as you go up. And something that I've been particularly looking at the moment is that we don't yet account for the temperature dependence of latent heats. And then one of the most important things that we're keeping the same is the whole time stepping scheme, which is called a semi-implicit semi-Lagrangian scheme, and I'll go into this on the next couple of slides. So the idea behind a semi-implicit time stepping scheme is that we're going to be able to take long time steps. So I've kind of written a toy version of our equation set here. So the whole equations can be split into transport, forcings, and then two types of physics that we call slow physics and fast physics. And the difference between those is how closely coupled they need to be to the dynamical core. And then this is kind of a quick version of how you would solve that semi-implicit time step. I've dropped physics for now because that does complicate things. But the idea here is it looks a bit like a Crank-Nicholson scheme if you've seen one of those. So we're going to evaluate our forcing term and make a difference on that at our nth time level. And then we'll transport it. So this curly T is like a transport operator. And then that's going to be equal to the same thing but evaluated at the next time level. And in a semi-Lagrangian sense, this corresponds to arrival points, and this part corresponds to departure points. So it's all about saying if we have a parcel of air here, we're going to try to solve it as it moves. And then this kind of terminology is a way of writing this in a kind of almost Eulerian sense. And the reason that we use this semi-implicit time-stepping scheme is that it allows large time steps stably, unlike explicit schemes. But a consequence of this is that we can get very large current numbers. So, for instance, in ELFRIC, with our 20-kilometer resolution model, we take time steps of 10 minutes, and that means our horizontal current numbers can be almost as large as 10. So we're essentially going to be transporting values of fields from 10 cells away in some parts of our domain. Okay, this is a kind of silly slide, but it's just kind of a demo of what our time-stepping scheme looks like. So this explicit forcing was that term on the right-hand side that we already know because we already know the nth level time variable. So we can evaluate our explicit things right at the start of our time step. So that's the forcing and slow physics. So we do those two things first. And then we enter a kind of complicated double-nested loop structure, which starts with a transport step and then moves to the fast physics, which is things like convection and the boundary layer, which have an implicit element in order to be able to handle large time steps. And then to tie together our implicit bit, oh, it's kind of skipping ahead. We have an implicit forcing and then a solve. Yeah, it got carried away. So I'll just go back on this bit. So this bit, this little circle, is another loop inside of itself, which is how we solve that implicit part. I've explained this quite quickly, but the important thing is that this is staying the same. So there we go. And then another thing that we've been talking about is dissipation mechanisms. So I thought I would mention what we do here. So because of our semi-implicit time-stepping structure, we've got kind of an implicit damping there. So we don't need an explicit dissipation scheme. But we do have damping through physics schemes, such as the boundary layer scheme, which do some diffusion, representing turbulence or mixing processes. The semi-implicit time-stepping scheme has an off-centering factor, so you can, if you need to, make things more implicit and more damped. Like every other model, I think we have a sponge or damping layer at the top of the model. And then finally, and kind of segueing into the next part of the talk, we do have upwinding and monotonicity in our transport scheme. Okay, transport. I told you I love lists, so here's another list. Things that we want from a transport scheme. So the first thing that we want from our transport scheme to work with our semi-implicit time step is it needs to be stable and efficient at large current numbers. And then I mentioned before, local mass conservation was one of these properties that we were really asked to get for the climate modelers. So the way that we do this is we solve our density transport in a conservative form. So writing this here as the divergence of rho times u. What we're going to take is a finite volume approach where we calculate fluxes that lie at the faces of cells. And this flux is written here as a capital F. And if we calculate a flux that lies at the edge of cells, we can then calculate a mass budget, because everything that leaves one cell will enter into another cell, and we get local conservation. How does this work for variables like mixing ratios that obey the advective form of the equation? So if you take the product of a mixing ratio m, which obeys the advective form of the equation, with a density rho, this together, this product, actually obeys a conservative form of the equation. And this brings me to my third property, which is consistency. So if you naively solve this equation, you might not be able to preserve a nice property of the advective form, which is that if m is a constant, then its gradient is 0, and it will remain constant for all time. If you naively solve this form of the equation, you'll get conservation, but you won't necessarily preserve that constant mixing ratio. And the way that we resolve this is that we substitute the flux here into rho times u, and we reuse the discrete flux from the density transport in the transport of our tracers. And what this means is that if m is constant here, then the divergence of this, the m pops out of the divergence, and you get m times the divergence of f. And if you solve this carefully enough, you can then still preserve your mixing ratio if it's a constant. Next comment is moisture can't go negative. And if you do just clip it, then you'll lose your local conservation. So managing to kind of handle both of those properties at the same time is really important. And then finally, I mentioned that our variables, we have this Charney-Phillips grid. So any transport scheme that we have has to somehow work on this Charney-Phillips grid. And I'm not really going to talk about how we do that, but it was a bit tricky. Okay, so we use a flux form semi-Lagrangian scheme. And so I mentioned that what this does is it involves calculating fluxes that are shared between cells. And each flux point has a corresponding departure point, and this is the kind of the semi-Lagrangian flavor. So you can imagine this flux point in the red, and then tracing this back to a departure point in blue. And then our flux is calculated basically by integrating the mass between the flux point and the departure point. And like a semi-Lagrangian scheme, this isn't limited by, its stability isn't limited by the current number, but also like a semi-Lagrangian scheme, there is still a number that defines stability for these models, and this is called the Lipschitz number. And if the Lipschitz number gets over 1, then all of the mass basically gets sucked out of the cell. And it turns out that this is now the stability criteria for our model, is the Lipschitz numbers rather than the current numbers. So in a flux form semi-Lagrangian scheme, what you tend to do is you tend to build up a multi-dimensional scheme by taking one-dimensional sweeps. And the state-of-the-art way of doing this has been used, it's been around for nearly 30 years, and you might know it as the Linen-Rude scheme. We call it the cosmic scheme. Part of the reason for this is kind of interesting, actually. So 2 sets of authors kind of discovered this scheme and published it in the same journal, in the same volume, both completely unaware of one another, although they kind of mention in the papers, and we have just become aware of this other work, which also is doing this. So these are basically the same scheme, but they have different names. We call it COSMIC, which is another acronym, because some of the authors were from the Met Office, and that's what they called it, so that's why we've always called it that, but you probably know it as the Linen-Rude scheme, which is used in FV3. So it's been used successfully because it's very accurate, it's very efficient, but there's a catch, and the catch is monotonicity. So with the Linen-Rude scheme, if you apply a monotonicity limiter to each of those 1D steps and then combine it, it will only still be monotonic if your current number is less than 1. And I guess that is the case for how FV3 is run, but unfortunately, that's not one of our principles or conditions. We have to make it work with larger current numbers. So what we're seeing here is a mixing ratio field, which has one of these slotted cylinders, and it's being transported by some highly deformational flow at a large current number of 5. And you can see that even though we're applying monotonic limiters, it's not monotonic. We're seeing all of these overshoots and undershoots in the magenta and the yellow colors. So we can't cheaply both obtain conservation and monotonicity with this scheme, and particularly this is a problem for large current numbers. So one of our kind of exciting developments from the last couple of years is that we've developed a scheme that we call SWIFT, which does resolve this problem. So some of my colleagues are actually unaware that SWIFT has a connection to my affections for a certain pop star, but I managed to sneak this by them and then make a backronym for it. So there we go. This scheme ensures both conservation and monotonicity just through applying a monotonicity limiter to each of the 1D steps. And the way that we do this is using a slightly different 2D splitting and slightly changing the definition of the departure points. And how I would describe this really is it's kind of just an evolution of the Linen-Rude scheme. And we originally designed it for tracers, but it's been quite successful, and now we use it for the transport of all of our variables. And I'm not going to go into this, but it can work then on the Charney-Phillips grid. We also use it for our potential temperature transport, which gives us something close to entropy conservation. And if you want to read some more, we've had a paper recently published about this in Monthly Weather Review. Okay, I think this is probably time for me to conclude. So I'll leave you with this list of design principles and then just summarize here what our dynamical core looks like. So we're using a cube sphere global mesh with a compatible finite element spatial discretization. Our transport scheme is a flux form semi-Lagrangian, and we still use a semi-implicit semi-Lagrangian time step. And I think I just have an animation to finish. So I'll take any questions. Thank you.
I guess this question could have occurred to me at any point today, but it just occurred to me now. If you have this like mass conservation between your cells horizontally that are squares, I can imagine you have a piece of mass in the corner of the cell that wants to move diagonally to the square of the element diagonal from it. Is that allowed, or do you just kind of split it into the face neighboring cells?
Yeah, I didn't mention any of the details of how this splitting Swift works, but what you do is you take 1D sweeps. So to go diagonally, that will be a consequence of going in the X direction and then the Y direction. So you'll kind of take a step in X and Y, and then it's an average of doing that in Y and then in X. Okay, so we'll transport mass to corner neighboring squares.
Yep. Okay, cool, thank you.
Yes.
In prioritizing stability for the user, do you guys have issues with too much numerical dissipation built in?
I'd say not, but I don't want to be controversial, but I guess we don't have this explicit diffusion in there. I've actually been recently looking at changing this off-centering parameter, which is one of the obvious ways that we can change dissipation. What happens when you do an evaluation like this is it can be kind of interesting because adding diffusion gives you, like we've seen in a lot of ML models, it smooths things out. You get better RMSE scores. So actually things at first look like they get worse by removing diffusion, even though you can predict features a bit better. I don't think that's really a great. You asked, do we prioritize stability? And I think our aim is to minimize the amount of diffusion that there is in the model in order to, but still have that stability. Yeah.
Go ahead.
One other question from the slide where you were showing the like drop a droplet in the middle with the different grids.
Yeah.
Like, very early on in the
Yeah.
presentation.
I've got a guess about what your question is, but I shouldn't put so many animations in, it takes forever to get back. Okay,
That
there we
one.
go. Yeah.
It just looks to me like for the quad C 2-1 that like the corners are slightly different. I'm wondering, I don't feel like I see that for like the triangle or the tri-C or the hex C. Well, I guess for the tri-C I see this sort of hexagonal pattern. Is that like grid imprinting or?
So
am I just
this,
seeing
yeah,
that?
this isn't grid imprinting, I don't think, because I think this is just done on a plane.
Oh, okay.
And so shouldn't really see artifacts there. I do think that it's actually the hexagonal one looks really impressive here,
Yeah.
despite having this extra wave mode from having the wrong number of degrees of freedom.
Right, but I kind of see like these corners, like especially towards the end, you see this like four-fold symmetry for the quad C.
Yeah.
Is that's not an optical illusion, that's actually a thing?
Yeah, yeah.
And it's an artifact from the shape of your elements?
I think it's the dispersion relation isn't perfect, so you still get some waves, but you don't get like the computational modes from like the A grid has.
Right.
Yeah.
Cool, thank you.
Yeah, go ahead.
Thanks for your talk. I want to ask a question about Swift.
Yeah.
So what is the key to combine the two properties, your conservation and motor?
Yeah. So
How to achieve that?
So PPM is a kind of the basic building block of doing a 1D flux form semi-Lagrangian scheme. We'll see if I skip to. Sorry. Okay, this. Yeah. So the key for getting monotonicity. So with conservation, all you have to do is make sure that everything is always the divergence of a flux. Every update is a divergence of a flux. Then you'll get conservation. In terms of monotonicity, what you have to do is when you do a reconstruction here in a cell where you've got your departure point lies in the middle of a cell, you have to do some reconstruction. You have to ensure that this doesn't create new overshoots and undershoots. And that's what you do to get 1D monotonicity and conservation. And then when you stitch this together to be 2D, you have to be really careful with what you pass from one step to the next step. And if you're really, really careful, you can ensure that you never create a new maxima or minima. So each thing always sees the same maxima or minima as the previous step. That's kind of a hand-wavy thing. If you want to read the paper, there's a bit where we prove that the different steps together still keep monotonicity. Yeah.
Can I add to that question? So I did a von Neumann stability analysis of the Lin-Root scheme a long time ago.
Yeah.
It showed it was weakly unstable for Courant numbers larger than 1. So if you turn on these filters, do you see any hint of that? For like running Courant number 5?
Yeah. No.
No?
No, but I think in the paper that you were talking about, you got quite close to the equation that we end up finding. That I'll talk to you about this later,
Okay.
maybe. But the equation that we use to stitch together the schemes.
Oh, okay.
Yeah.
It was a question.
I had a question about the trick that you used to ensure that mass was conserved and also it preserves the advection property.
Yeah.
So if you use F from the density, so now that you have M rho and M, two different variables in the equation, so do you also use the density from?
Yes, yeah, we do, yeah. Yeah, so we first transport the density. That gives us like the density at the start of the time step, the flux used to transport it, and the density at the end of the time step. And then you use those three things in the transport of the traces.
And it's still different from just subtracting off the density equation of using the product.
Yeah, so actually we do kind of divisions of density. Yeah.
Christiane?
Yeah, actually, same question that I asked Mark. How do you include moisture into your deco, and what's your thermodynamic variable?
So we actually use the dry potential temperature.
Right?
But for transport, where we transform to the virtual dry, transport that. The reason being it's slightly smoother, and so you get a slightly better representation of the tropopause by transporting that. You can still preserve a kind of sharper edge in the dry potential temperature. But we do the same thing that our external pressure is still dry, our kappa is a constant, kappa doesn't include moisture.
Okay, Marnie?
Yeah.
This would be a question actually like more for Christiane and for you, but why is like virtual temperature the next logical step and not equivalent potential temperature if we were to include moisture?
Equivalent potential temperature's got a really, really horrible definition. So it makes the equations look really horrible. And that's why I think it would be possible to kind of back it out, like what you're... So the idea would be you transport the equivalent potential temperature, and that takes into account like the latent heat exchanges and the phase changes, and it's still preserved while those exchanges and changes between phases have happened. But then you would need to back out from that what the amount of vapor and cloud and ice were at the end, and the process of backing that out is really nasty, and what your pressure gradient term would look like with that variable would be really nasty. So I think it may well be possible, and it may well be that that gives the best thing, but people have just been so scared, I think, of doing it, because it's really complicated. Yeah.
Alrighty.
Can I
Last
ask a
question?
related question? Is that variable, I'm not familiar with that variable, but is that also an entropic variable, or is it?
I've always assumed that it is, yeah.
So before we clap for Thomas, Jesse up here behind the screen had to rush back to make sure we could get the live stream up and running and do the presentations this afternoon. So let's give him a hand first. Please keep an eye. I've edited the schedule to reflect what happened today. We're trying to move up the talks, so we have talks in the morning and then practical sessions, but everything is a little bit in flow right now, so keep an eye on it. And the class is still at the same time.